Hi, everyone. This is the Energy Sharing and Management System team. My name is Mindy Saylors, and we have Jingjing Shou, Chahao Li, and Sadvik Anand. So to talk to you a little bit about the problem we're addressing, today the market for home renewable energy generation is growing quickly, with homes wanting to either support the renewable energy generation industry and or maybe just want to make their energy supply more reliable. The fact of designing a system for a reliable electrical load is always an issue. Also, the cost of energy is something that can always be improved upon. Common approaches to these are to scale your energy generation in tandem with your storage capabilities, but to best suit your home energy's electrical load profile. Even if you're willing to pay for more generation than you can use, you still can't. It's a hard scaling profile. Even if you're set up to sell energy back to the grid, sometimes you can't send this back to the grid for stability purposes. You have static peer-to-peer trading to alleviate these grid operation issues, but something you can also set up is a local energy storage system through the grid's network. We'll get into further detail on how these systems can be utilized in this project, but I'll hand it over to Satvik to address current research.
Thank you, Mindy. State-of-the-art research in energy management systems focuses on using reinforcement learning variations or deep learning. These systems can be modeled by MDPs, where an agent, which is one of the components of the energy management system, has to make decisions about how to allocate and acquire energy so as to achieve optimal prices for the users along with optimal energy consumption. The reinforcement learning approach in energy management is an emerging field based on the bibliometric analysis research. This graph shows the increasing number of publications in this field within the past decade. After doing literature review, our project narrows down to implement a smart energy system with MDP and Q-learning approaches. To better understand the approaches of implementing reinforcement learning for an energy sharing community system, our literature review mainly focuses on two parts. The first part is the mechanism for the energy sharing system, including the battery energy storage system, community pricing model, and peer-to-peer trading system. The second part is the potential method or algorithm of approaching this smart system, including MDP process, reinforcement learning, which can include Q-learning and fuzzy Q-learning, and Gaussian process regression to improve our results. I'm going to pass it on to Jingjing.
Thank you, Savit. After down literature review, let's focus on our problem. Our project is to create a smart residential community where the agent can make decisions for users to trade with the local energy pool or markets to enjoy the cheap renewable energy based on the environment. As shown in Figure 3, there are 4 parties in our system. The smart homes are equipped with the energy storage system. This system can help the smart homes to sell the surplus energy to the energy pool or buy the energy back from the pool with the consideration of the real-time energy price. Non-intelligent homes, they can buy the energy from the energy pool with a relatively lower prices than the retail market price, and can also buy the energy from the retail market when there is no sufficient energy available. Agents will make decisions and do actions. They do charging-discharging decision at every stage for energy storage system and do buy or sell energy action for neighborhoods. The local energy pool, they can harvest surplus energy from users and renewable resources, which is solar energy in this case. At the same time, it sells energy at a price between the feed-in tariff and the retail price. For better understand and define our system, there are some mechanisms and expressions to define our relevant subsystems. 2 models are introduced here on slide. Battery capacity model is used to describe our energy storage system, which is the key controllable equipment. The model shows the constraints and dynamic changes. Charging-discharging rate, efficiency, and maximum charging-discharging rate are main factors in this ESS model. The community price model, another key model, is also shown here. The model contains several parameters, including surplus versus demand ratio, rest energy, energy sold by energy pool, and generated solar energy, etc. Finally, these community prices should be controlled between the real-time price and feed-in tariff. It is a planning problem for our system regarding to our objectives and goals, especially as described in the problem statement before. Our project is aiming to helping neighbors to make decisions to minimize the cost in this community. The goals and deliverables are defined. Our final deliverable for project should have firstly, result table showing agent making dynamically actions for storage system, which is by doing charging or discharging actions. Secondly, a result graph should show trading action that the agent makes for users within the community. Lastly, the cost comparison data table should show evident minimized mean value result for smart community with these applied algorithms. The planning method approaches including MDP, fuzzy Q-learning, and Gaussian process will be discussed later. This planning method to solve for P2P trading in our particular system can be extracted and utilized for various energy management problems, especially those who had the same constraint with our system. For example, use of fuzzy Q-learning to discretize the continuous state space to discrete space.
I'm going to talk about the mathematical formulation. Based on the problem statement, our energy trading process can be modeled as an MDP problem. To formulate the MDP, we define the state space and action space for the system as shown here. Our state space is given by three values, S1, S2, and S3. S1 is the battery capacity, S2 is the real-time retail price, and S3 is the community market price. Our action space is given by AS and AT. AS is the action taken to charge or discharge the battery capacity as a percentage of the maximum charge or discharge rate. AT is the amount of electricity traded as a percentage of the maximum electricity trade rate. The maximum charge or discharge rate and maximum electricity trade rate are known values. In this problem, we are unaware of our state dynamics and sensor model, and we don't need to know these for our Q-learning algorithm. Our reward function is formulated for a particular combination of actions at a particular state value. The reward function is given by these equations, which forms a relationship between the electricity traded with the local pool, the community market price at that state, the retail price at that state, the home energy demand at that time, and the amount of electricity that the battery charges or discharges at a time instant. We can then normalize this value in the range 0 and 1. We set our discount factor in the MDP to 0.9. I'm going to pass it on to Chao Hao to talk about the design process.
Thank you, Savik. Now let's move on to our design process on this project and some decisions we made during the process. After thoroughly understood the concept behind the energy sharing community, especially the pricing model and the battery charge or discharge model, we started to evaluate the MDP introduced by the community sharing paper. Then we changed the trade action space to make it include both buying rate and selling rate, instead of only having the trade rate, which made our MDP to be more reasonable. When we finalized our MDP modeling, the first thing we did after that was to implement the energy sharing community based on the fuzzy Q-learning algorithm. The reason to do the implementation first is so that after an implementation, for every change we make, we can have a better knowledge of how the system gets improved after that change. During the process of implementing fuzzy Q-learning algorithm, we noticed several problems. First, the input action set for our MDP has two separable action sets instead of one, which is not common. The limits of some variables in that system are not well declared. Third, some terms that the paper used were unclear, making it harder for the actual implementation. Based on what we have learned from this class, we made some decisions to solve these problems. First, unlike most normal Q-learning process, for this fuzzy Q-learning algorithm that has two different input action sets, we need to change the dimensions of the corresponding little q value table to be larger. And instead of having one action from the action table to match the q value table, we implemented combined action to match the value in q value table. And that solved the problem. Second, there's one variable in the system that doesn't have the limitation or any useful information, which is capacity of the local energy pool. So we made our decision to set it to be multiplication of number of users and the potential power that each user may consume. Since each user's battery has 13.5 kilowatts, we set the potential usage to be 20 kilowatts for each user. There are two logics that are left ambiguous in this paper. The first one is that we don't know if the solar energy generated and the electricity demand for every iteration should be included in the charging or discharging action or not. For now, we didn't include it into the battery storage model because it's not specified in the function. Secondly, we're also not sure about the term used in the paper, which is the maximum electricity trade rate. To move forward, we made the assumption that the maximum electricity you can trade is the amount of charge we discharge or charge at a certain time instant, so that we can be sure about the amount of charge we trade at different trade rates. Our next step will be to implement the Gaussian process regression on the data we are fitting in. Mindy will talk more about it in the later section, the future work. The use of fuzzy Q-learning. This fuzzy Q-learning consists of three main parts. The first part is to complete the fuzzy output set for our states. Then we can convolve them together to get our little q value table, where each value in this table is corresponding to a combination of storage action and trade action. The second part is the Bellman backup, where we accumulate the value for the large Q and the value function v and update them. Then we apply and select the optimal action combination to further update our Q value. The last part is the exploration and exploitation algorithm. We use it to help our agent perform better. and also we use it to make sure we can find the potential optimal combination of actions. Now let's look at current result of our implementations. After successfully implemented the algorithm, we tested within 8,600 iterations, and each iteration represents a 30 minutes interval. These are the actions our agent took responding to the pricing change and also the electricity demanded for every iteration. Some truths we found from looking at these graphs are: first, our agent was able to trade with the local energy pool at the maximum rate when the solar energy generated plus the battery capacity is higher than the electricity demand, which meet our expectations. Second, when there are more changes in the local energy pool, the community drops rapidly and sometimes goes to negative, showing our objectives of letting users use more renewable energy. Also, when the community price is a lot lower than the retail price, our agent is able to charge its battery by buying from the local energy pool. However, there are some irregularities we notice in our graphs. First, the plot of the storage actions has some kind of a periodic change, which might show that our implementation is not responsive that well. Second, the state of charge is not changing responsive of the solar energy data or the electricity demand data. We could say it's rather changing only responsive to the charge or discharge action, which doesn't make a lot of sense. But since we're only using 2 users' data, and the electricity demand data might not match the solar energy data that well, we'll be testing more dataset and a larger dataset to see what happens to our model in the future. Now I'll pass it to Mindy to talk about our future work.
Thanks, Xiaohao. Talking for our future work to be completed for the report, we plan to apply the Gaussian process regression technique to our solar and home electrical load profiles, and also edit our state space with this, along with the action space. This is just to make a more realistic model, and the action space is pretty important. We hope that works well enough. Then there's also, to evaluate that GPR, we need to do a mean square error evaluation. Then another fix is our pricing model for energy generation at the home. There's also remaking the reward function to be based on the average price per kilowatt for smart and non-smart users. And there's also reason for average price reward is to bring down the cost of energy. Renewable energy penetration is to incentivize trading with homes selling renewable energy, because hypothetically any smart user could be selling energy in this market even if they produced it for their coal burning stove from their coal burning stove. There's also a cost of renewable energy penetration comparison. And lastly, we'll apply our Q tables to large systems to see how that algorithm scales. And our expected conclusions are applying the GPR and updating the pricing model. We expect it to be more realistic. Our current setup, the action space is very limited, and it's not realistic to how energy trading actually works. The agent should be able to continuously update the trading rate whenever they see fit, and not be limited to a trade fixed rate in 30-minute intervals. Currently, the monetary value of the energy traded for a home is set specifically related to the retail price without any analysis of the production cost of that specific energy source. Changing this will help adjust that reward function bias for our energy generation. For the renewable energy reconstruction, we of course should see drastic changes in the agent actions. It's currently based on the amount of energy traded which is extremely arbitrary. We're not entirely sure if the renewable penetration will function to improve the agent's actions all that much. Cost may be enough. So that's all we may need. For our cost analysis, we expect to significantly improve the energy price and renewable energy penetration, of course, without the algorithm. Finally, we're not certain about how this Q learning algorithm will scale, but certainly hope for the best. And here are citations right here. These are some of additional references we've used for our data sets. And thank you for listening, and hope you enjoyed the presentation. Any feedback would be greatly appreciated.